Bismillahirrahmanirrahim. Assalamu alaikum everyone. My name is Sauood Siddiqui. I am from the Department of BS Biochemistry and my roll number is 003. Today I am going to deliver a short presentation on the topic of acid-base concepts, the Bronsted-Lowry theory and acid and base strength. My resource person is Sir Hammad Majeed. Let me begin with a general introduction of acid and bases. Acetic acid in vinegar, citric acid in lemons and other citrus fruits, magnesium hydroxide in commercial antacids, and ammonia in household cleaning products are among the acids and bases that we encounter in our everyday life. Hydrochloric acid of approximately 0.15 molar concentration is the acid in the gastric juice. It is essential for digestion and is secreted by the lining of our stomach in the quantity of 1.2 to 1.5 liter per day. If I talk about the general properties of acid and base, acids react with metals such as iron and zinc to yield hydrogen gas, and they change the color of plant dye, which is litmus paper, from blue to red. By contrast, bases feel slippery and they change the color of litmus from red to blue. When acid and bases are mixed in the right proportion, the characteristic acidic and basic properties disappear and we obtain a new substance which is known as salt. Before coming to my main topic, let me give an overview of Arrhenius concept. According to Arrhenius, acids are substances that dissociate in water to produce H positive ion, and bases are substances that dissociate in water to yield OH negative ion. Thus, HCl and H2SO4 are acids, and NaOH and BaOH twice are bases. Here is the generalized equation of Arrhenius concept, but this concept has some limitation. First, the Arrhenius theory is restricted to aqueous solution. Second, it doesn't account for the basicity of substances like ammonia that don't contain OH group. To overcome this problem, in 1923, a more general theory of acids and bases was proposed independently by the Danish chemist Johannes Bronsted and the English chemist Thomas Lowry. According to Bronsted-Lowry theory, an acid is any substance, molecular ion, that can transfer a proton, which is H positive ion, to another substance, and a base is any substance that can accept a proton. In short, acids are proton donors, bases are proton acceptor, and acid-base reaction are proton transfer reaction. Here is a reaction given in which you can see acid in the red and bases in the blue. Acid donates proton and base accepts a proton. Now, what is conjugate acid-base pair? Chemical species whose formula differ only by one proton are said to be conjugate acid-base pairs. Thus, in the reaction given below, A negative is the conjugate base of the acid HA and HA is the conjugate acid of the base A negative. Similarly, B is the conjugate base of the acid BH positive and BH positive is the conjugate acid of the base B. When a Bronsted-Lowry acid HA dissolves in water, it reacts reversibly with water in an acid dissociation equilibrium. The acid transfers a proton to the solvent, which acts as a base. That is, water accepts an proton. The products are the hydronium ion H3O positive, which is the conjugate acid of H2O. H2O, that is water, reacted as a base and it produced the conjugate acid, and A negative is the conjugate base of the HA, which is an acid. So these are the conjugate acid base pairs. You can see in this slide the reaction is written and the conjugate acid base pairs are shown. In the reverse reaction, H3O positive can act as a proton donor and A negative can act as a proton acceptor. Typical example of Bronsted-Lowry acids include not only electrically neutral molecules such as HCl, HNO3 and HF, but also cations and anions of salts that contain transferable protons such as NH4 positive, HSO4 negative and HCO3 negative. Now, when a Bronsted-Lowry base such as NH3 dissolves in water, it accepts a proton from the solvent, which acts as an acid. So NH3 will act as a base. The products are the hydroxide ion, OH negative, the conjugate base of water, because water donated a proton, so water will act as an acid. The ammonium ion NH4 is the conjugate acid of NH3 because NH3 originally accepted a proton, so it will act as a base and NH4 will be the conjugate acid of the NH3. Here you can see the reaction. Now for a molecular ion to accept a proton, it must have at least one unshared pair of electrons so that it can use for bonding to the proton. As shown by the following electron dot structure, all Bronsted-Lowry bases have one or more lone pair of electrons. You can see in water, in fluoride ion, in ammonia and in hydroxide ion there are all lone pairs are shown. Now let's talk about acid strength and base strength. A helpful way of viewing an acid dissociation equilibrium is to realize that the two bases H2O and A negative are competing for proton. For example, if we have an acid HA and it reacts with water H2O, it will form H3O positive plus A negative. So H3O positive will be the conjugate acid of base H2O. If H2O is a stronger base, which is a stronger proton acceptor than A negative, which is the competing base, then H2O molecule will get the protons and solution will contain mainly H3O positive and A negative. But if A negative is a stronger base than water, then A negative ion will get the protons and the solution will contain mainly HA and H2O. This is the simple mechanism. When beginning with the equal concentration of the reactants and products, the proton is always transferred to stronger base. This means that the direction of reaction to reach equilibrium is proton transfer from the stronger acid to the stronger base to give the weaker acid and the weaker base. So the proton will be transferred from stronger acid and base will accept it, and in turn we will get weaker acid and weaker base. It is shown by the reaction. Different acids differ in their ability to donate proton. A strong acid is one that is almost completely dissociated in water and therefore a strong electrolyte. So electrolyte is one solution that can dissociate in its ion. Thus, the acid dissociation equilibrium of a strong acid lies nearly 100% to the right, and the solution contains almost entirely hydronium and A negative ions with only a negligible amount of undissociated HA molecules. Typical strong acids are perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. It follows from this definition that strong acids have very weak conjugate bases. The ion chlorate, chloride, bromide, iodide, nitride, and HSO4 negative have only a negligible tendency to combine with a proton in aqueous solution, and they are therefore much weaker bases than H2O. A weak acid is one that is only partially dissolved in water and is thus a weak electrolyte. Only a small fraction of the weak acid molecules transfer a proton to water, and the solution therefore contains mainly undissociated HA molecules along with small amounts of hydronium and the conjugate base A negative. Next, we have the example of typical weak acids. Typical weak acids include nitrous acid, hydrofluoric acid, and acetic acid. In the case of very weak acids such as NH3, OH negative, and H2, the acid has practically no tendency to transfer a proton to water, and the acid dissociation equilibrium lies essentially 100% to the left. It follows from this definition that very weak acids have strong conjugate bases. For example, the NH2 negative, O2 negative, and H negative ions are essentially 100% protonated in aqueous solution and are much stronger bases than H2O. Here we have some diagrams showing the strength of acid, and they depict which is strong acid, which is weak acid, and very weak acid. You can see in this diagram the extent of dissociation is nearly 100% for a strong acid, but for weaker acid it is considerably less than 100%, and for very weak acid it is nearly 0%. While in the last slide we have some chart which shows the which shows the acid and their strength and bases and their strength. So that's all from my side. Thank you. Allah Hafiz.